All right, welcome, ladies and gentlemen. I'm going to introduce half-life to you. So you'll want to find in your notes, have the section open where we first has the half-life heading, not the video, but just the half-life heading. And we're also going to need our reference table for this. So half-life. Half-life you've seen before in earth science. And so just as a reminder, half-life is the time required for 1/2 of the nuclei in the radioisotope sample to decay to its products. So what does that mean? Well, first of all, its products, I want to point out, when we say decay to its products, well, the radioisotope, that sucker is radioactive. Its products are not. So half-life, in most cases, the products are not. There's a few that has to go through a series of reactions. But half-life is essentially saying how long does it take for half of your sample to become no longer radioactive, i.e. to become not radioactive, to become stable. So for example, we're going to do phosphorus 32. I might have had carbon 14 in the notes, but I'm going to change it up to P32 because I used to work with P32. So it's very near and dear to my heart. P32. So if we want to write essentially the nuclear decay equation for phosphorus 32, because it is a radioisotope. Well, phosphorus is P. And remember 32, that's the mass number. And we want to get the atomic number, and that's coming off of the periodic table. So we look up P, and that's 15. Now this guy's radioactive. But as time goes on, it decays. It decays, and that's that natural transmutation, right? Natural transmutation, it naturally emits a particle in order to become stable. And we want to figure out how it decays. So you want to go to table N. Table N is your friend. We're going to write the reaction, the natural transmutation reaction for this. And we look up what type of particle does P32 emit. So you want to find phosphorus 32 on there. And hopefully you see that it is a beta emitter, right? It emits a beta particle. So beta particle symbol 0, -1, and the beta sign you could also write an E there. That works too. So it gives off that particle, and we want to figure out the missing one. So remember, some of the mass numbers on each side must be equal. So 32 is equal to 0 plus something. Well, that must be a 32 there. And then the atomic numbers are also equal. So 15, right, the sums are equal, is equal to -1 plus what? 16, not 14. 14 plus a -1 is 13. That is not equal to 15, right? 16 plus a -1 is equal to 15. And then we fill in the symbol. Well, what symbol is atomic number 16? We go and we look at the periodic table again, and that is sulfur. So this is the beta decay, the natural transmutation of P32. Now, half-life, to bring it back to half-life, this sucker is radioactive. And this is the radioactivity that it gives off, that beta emitter. And we've talked about how it has sort of a medium penetrating ability. Skin doesn't stop it, but a slightly thick piece of plastic or aluminum foil, it will. But this product, this is stable. This is not radioactive. And half-life is how long it takes for half of a sample of phosphorus 32 to undergo this process. So we go back to table N, because table N actually lists half-lives for a whole bunch of different radioisotopes. And if you look up P32, you'll see that it says the half-life of P32 is 14.28 days, which is a relatively short half-life, all things considered. And that means that if you have a sample that's fresh of P32, meaning it's all radioactive, and you let it sit for 2 weeks, which is just about its half-life, at the end of those 2 weeks, only half of it is going to be radioactive. If you let this sample sit for 4 weeks, that's 2 half-lives. It's not going to be 0 radioactivity. You're going to be continually taking half of half of half of half, etc. 2 half-lives. After 1 half-life, 50% of it is now going to be radioactive. But after a second half-life, only 25% of it's going to be radioactive because you took half of what you had. Right? It's always the taking half of what you had. And this actually meant that when we were dealing with the P32 in the lab, because it had a relatively short half-life, we would get the p32 in, we'd use it for tagging the DNA and looking at the DNA because of DNA's phosphate backbone, so p32 is kind of a natural tagger to visualize DNA. We literally had in the corner of a lab, we had a wastebasket that we had essentially coated in, it was covered in about a 2 centimeter thick piece of lead on all sides. So it was our lead wastebasket, and it had a lid too. And all we would do to dispose of the p32 is we put all the contaminated like tubes and stuff into the bin, and we'd just let it sit for like 6 months. And then at the end of 6 months, we could throw it out, because by that point, by 6 months, it had decayed so much that the radioactivity was essentially the same as just background radiation, like normal radiation that we're exposed to every day. So we would just kind of wait out the half-life. We just keep on letting it sit and letting it sit and letting it sit to the point where enough of it had decomposed and was no longer radioactive. It had turned into a stable isotope that we could simply dispose of it just in the regular trash, which I always thought was really funny. It's like we have this radioactive waste, so our solution is we'll just wait it out. Now you can't do that with every radioisotope, because if you have ones that have much longer half-lives, well, you can't wait it out. But we could, because this half-life was only about 2 weeks. So that's my fun story. It was interesting working with p32. So as an example of half-life, to go back to this idea of half-life of rubidium-87 is about 60 billion years. Okay, so this is something that you could not wait out, right? 60 billion years. That's really long. You can't just wait that one out. But to start with, if we have a sample, and initially a sample of rubidium-87, all of it is going to be radioactive at the beginning. So what I want you to do here is just kind of shade in this whole sample, because this is going to be like our sample of rubidium-87. To start with, all of it is radioactive. But after 60 billion years, well, this is one half-life. So half is still radioactive, but half of it isn't. Half of it has become stable. So now we're only going to shade in half of it. We're not going to shade in the entire thing to indicate that now only half of it is radioactive. The other half has become stable because we've let it sit for one half-life. After 120 billion years, well, this is 2 half-lives. And I mean 120 billion years since starting. Well, after 2 half-lives, only half of half is still radioactive. So it hasn't gone to 0, because with each half-life you are taking half of whatever you remained. So after 2 half-lives, we're basically saying we're starting with that, half of that we had is now going to still be radioactive. Half of half, aka 1/4. Right, 1/4 of it is still going to be radioactive, so you're only going to shade in 2, and the rest of it has become stable. After 180 billion years, this is 3 half-lives. So after 3 half-lives, half of half of half, taking half 3 times, is still radioactive, which is the same thing as not 1/6, but 1/8. Right, half of this is still radioactive, so that we're only coloring in 1 square. With half-life, it's about constantly taking half of whatever remains, which theoretically means that you can never get to 0, right? If you're talking philosophically, if you keep on taking half of a half of a half, right, it'll keep on going. But practically speaking, it means that you get to a point where so little of it is radioactive that it kind of just blends into the background radiation that we're used to in our normal everyday life. So another example with this half of a half idea is we have this circle, and we want to get really familiar with the fractions and the percents that are super common in half-life problems. So a sample will always start with 100% or the whole being radioactive. So we always start with 100%. The fraction version of 100% is 1. Right? The whole thing, 1. It's a fraction, you know, 1/3, 1/6, 1/8. Well, it came from 1. If you let it sit for 1 half-life, So this circle sort of represents our whole. If we let it sit for 1 half-life, then we divide the circle in half. So, right, you have half. So the 1 would turn into 1/2. And I'm going to put a 1 there, and that's going to mean 1 half-life. In terms of percents, because we see both fractions and percents when we're dealing with half-life, after 1 half-life, we go from having 100% of our initial to having 50% of our initial, right? You take half. But we're going to let this sit some more. So after 1 half-life, we have half. But after 2 half-lives, now we're going to take half, and now we're going to split it in half again. Right? Take the half, split it in half again. So the 1/2, we're taking half of that. So now we get 1/4. Right? And I'm going to put a 2 here, indicating 2 half-lives total. Right? 2 half-lives total. 1, 2. And then again, if I take half of 50%, what's half of 50%? 25%. So after 2 half-lives, you have 1/4 or 25% remaining. If we do this again, if we take half of the remaining, we're going to take the remaining bit, split that in half. So 1/4, after a total of 3 half-lives, that's going to become 1/8. So this is 1/8. 25%, we're going to take half of that. 25%, half of 25% is 12.5%. So that's how much we'd have for that after that 3rd half-life. If we let it sit for a 4th half-life, we are going to once again take half of the remaining. So that's going to be now 1/16. And we're going to take half of 12.5% after 4 half-lives. That's 6.25%. And we can keep going with this. So I'm going to take half of 1/16. So I'm splitting that last section in half, not very exactly, but that right there, that is 1/32. So that 5th half-life, I'm going to have 1/32 remaining. And over here, if I divide that 6.25 by 2, again, take half of it. You're constantly taking half of your amounts. That turns into 3.125%. And so on and so forth. Like, you can keep going. This can absolutely keep going. You get 1/64th and 1/128th, etc., 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 but you're constantly taking half of what you have. Now, for each half-life, 1/2 of the substance decomposes. If we start putting numbers with this with actual amounts, if we take an example of radium-234, its half-life is 3.6 days, which is pretty short. So if you start with 50 grams of your radium-234, that's your stuff that's radioactive, right? All 50 grams of that would be radioactive. If you let it sit for 3.6 days, which is 1 half-life, the amount that's going to still be radioactive at the end of that is going to be half of it. So 25 grams would still be radioactive at the end of that period. The rest of it would have turned into something else, something that isn't radioactive and is not radium-234. It's different in some way. It's changed. It's undergone that transmutation. It has changed the nucleus. But the way that you're going to see me write it is like this, kind of like I was doing in the last one. 50 grams goes to 25 grams, and I'm going to put a little half sort of on top to indicate that we're taking half of it, right? That 1 half-life. So 50 grams, it underwent 1 half-life time span, and now I have half of it remaining. And each arrow, when you see me write this arrow, which I'm definitely going to be doing, it means I'm taking 1 half-life, so I'm dividing my amount by half each time. I'm sorry, dividing it by 2, or taking half each time. So after 7.2 days with this 50-gram sample of radium-234, well, that's 2 half-lives. So I'm taking half of the original amount. So I'm going to have 12.5 grams left, or the way that I'm going to write it out is 50 grams, take half of it, you get 25, take half of that, you get 12.5. So each arrow kind of represents that 1 half-life time span, right? The first half-life was the 50 grams to 25 grams, but then the second half-life was the 25 grams to the 12.5 grams. Each arrow, I'm just taking half. After 10.8 days, which is time span allowing 3 half-lives to elapse, we're basically going to do this 3 times. For 3 half-lives, we're going to take half of half of half, i.e. 1/8. We get 6.25 grams. Or the method that I'm going to use, 50 to 25, that's the first half-life. 25 to 12.5, that's the second half-life. 12.5 to 6.25, that's the third half-life. And after each half-life, I'm taking half. That's literally what half-life means. You take half. And the absolute key thing to half-life questions, which is going to be in your video that you have to watch for Tuesday, you have to ask yourself how many half-lives have elapsed. If you can figure that out, you can work through the half-life problem. This is rarely going to be the actual answer to the problem. Rarely does the question ask how many half-lives have elapsed. Usually they'll ask things like how much mass is left or how long has it been sitting. But I guarantee you the key to answering that is first in answering this question, how many half-lives have elapsed. So this is really sort of the big thing that you have to think about. Now, in terms of the math with half-life problems, there's going to be a lot of numbers, and that's what you'll see in the next video. Crucial thing is, though, is you're allowed to divide time by time, meaning you can divide a total time by a half-life time, but you can never divide grams by grams. You can't do that. No, 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 no. You can only ever divide grams by 2, meaning you can only take half of your mass, because that's in part of the definition of half-life. You're taking half of your amount, half of your amount, half of your amount every single time. So if you have mass with half-life, you're just constantly taking half of your stuff.